Exponential generating functions, recurrence relations, and exponential generating functions. Not all recurrence relations can be turned into a closed formula by using an ordinary generating function. Sometimes a closed formula may not exist. Some other times, it could be that we have to use a different kind of a generating function. Example 8.17. Let a0 equals to 1 and let an plus 1 equals to n plus 1 times an minus n plus 1. If n is greater than or equals to 0, find a closed formula for an. If we try to solve this recurrence relation by ordinary generating functions, we run into trouble. The reason for this is that this sequence grows too fast, and its ordinary generating function will therefore not have a closed form. Let us instead make the following definition. Definition 8.18. Let Fm braces with n which is greater than or equals to 0 be a sequence of real numbers. Then the form of power series f of x, which is equals to the summations of fn times x to the n over n factorial, summing for all n which is greater than or equals to 0, is called the exponential generating function of the sequence fn braces with n which is greater than or equals to 0. The word exponential is due to the fact that the exponential generating function of the constant sequence fn equals to 1 is e to the x. Let us use this new kind of a generating function to solve the example at hand. Solution of example 8.17. Let a of x equals to the summations of an times x to the n divided by n factorial, summing with n starting from 0 to infinity, be the exponential generating function of the sequence an braces with n which is greater than or equals to 0. From this point on, we proceed in a way that is very similar to the method of the previous section. Let us multiply both sides of our recursive formula by x to the n plus 1 divided by n plus 1 factorial, and sum over all n which is greater than or equals to 0 to get the summations of an plus 1 times x to the n plus 1 divided by n plus 1 factorial, summing for all n starting from 0 to infinity is equals to the summations of an times x to the n plus 1 divided by n factorial, summing with n starting from 0 to infinity, minus the summations of n minus 1 times x to the n plus 1 divided by n factorial, summing with n starting from 0 to infinity. Note that the left-hand side is a of x minus 1, while the first term of the right-hand side is x times a of x. This leads to a of x minus 1, which is equals to x times a of x, minus x squared times e to the x, plus x times e to the x. A of x is equals to 1 over 1 minus x plus x times e to the x, which is equals to the summations of x to the n, summing for all n which is greater than or equals to 0, plus the summations of x to the n plus 1 divided by n factorial, summing with all n which is greater than or equals to 0. The coefficient of x to the n over n factorial in the summations of x to the n, summing for all n which is greater than or equals to 0, is n factorial, while the coefficient of x to the n over n factorial in the summations of x to the n plus 1 over n factorial, summing for all n which is greater than or equals to 0, is n. Indeed, this second term summoned the term x to the n over n minus 1 factorial. Therefore, the coefficient of x to the n over n factorial in a of n is an equals to n factorial plus n. Example 8.19. Let f0 equals to 0 and let fn plus 1 equals to 2 times n plus 1 times fn plus n plus 1 factorial if n is greater than or equals to 0. Find an explicit formula for fn. Solution. Let f of x equals to the summations of fn times x to the n over n factorial, summing for all n which is greater than or equals to 0, be the exponential generating function of the sequence fn. Let us multiply both sides of our recursive formula by x to the n plus 1 over n plus 1 factorial, then sum over all n which is greater than or equals to 0. We get the summations of f n plus 1 times x to the n plus 1 divided by n plus 1 factorial, summing with n which is greater than or equals to 0, which is equals to 2x times the summations of fn times x to the n divided by n factorial, summing for all n which is greater than or equals to 0, plus the summations of x to the n plus 1, summing for all n which is greater than or equals to 0. This is formula 8.14. As f0 equals to 0, the left-hand side of 8.14 is equal to f of x, while the first term of the right-hand side is 2x times f of x, and the second term of the right-hand side is x over 1 minus x. Therefore, we get f of x equals to 2x times f of x plus x over 1 minus x. And we can do the manipulation to get f of x equals to x over 1 minus x times 1 minus 2x. So therefore, f of x is equals to the summations of 2 to the n minus 1 times x to the n, summing for all n which is greater than or equals to 0. And so the coefficient of xn over n factorial in f of x is fn, which is equals to 2 to the n minus 1 times n factorial.